Welcome to lesson 9 of our discussion of the network layer in the course Networks and Distributed Systems. Based on the textbook by Jim Carose and Keith Ross, Computer Networking, a Top-Down Approach. We are going to talk about another issue about addressing. It's network address translation. So let's get started. Given our discussion about the Internet addresses in the IPv4 datagram format, we now know that every IP-capable device needs an IP address. With the proliferation of small office, home office subnets, and so on, this would seem to imply that whenever an office wants to install a LAN to connect multiple machines, a range of addresses would need to be allocated by the ISP to cover all those machines. If the subnet grew bigger, a larger block of addresses would have to be allocated. But what if the ISP has already allocated the contiguous portions of the network's current address range? Fortunately, there is a simple approach to address allocation. It's the Network Address Translation, NAT. This figure 4.22 that you see here shows the operation of a Nat Enabled Router. The Nat Enabled Router residing in the home has an interface that is part of the home network. Addressing within the home network is exactly as we have seen before. All four interfaces in the home network have the same subnet address of 10.0.0/24. The address space 10.0.0.0/8 is not a public IP address. It is one of three portions of IP address space that is reserved for a private network or a realm of private addresses, such as the home office network in this figure. Another such range that you may find being distributed by your home wireless router is the 192.168.0.0/16 range, also private. A realm of private addresses refers to a network whose addresses only have meaning to devices within that network. To see why this is important, consider the fact that there are hundreds of thousands of home networks, many using the same address space, 10.0.0.0/24 or 192.168.0.0/16. Devices within a given home network can send packets to each other using either of these address ranges. However, packets forwarded beyond the home network into the larger global internet cannot, because there are hundreds of thousands of networks all using this same block of addresses. That is, these two ranges of addresses can only have meaning within the given home network. But if private addresses only have meaning within the given home network, how is addressing handled when packets are sent to or received from the global internet, where addresses are necessarily unique? The answer to this question lies in understanding NAT, Network Address Translation. The NAT Enabled Router does not look like a router to the outside world. Instead, the NAT router behaves to the outside world as a single device with a single IP address. In that last figure, all traffic leaving home router for the larger internet has a source address of 138.76.29.7. And all traffic entering the home router must have a destination address of 138.76.29.7. This is a global public internet address. The NAT Enabled Router is hiding the details of the home network from the outside world. If you are wondering where the home network computers get their addresses and where the router gets its single IP address, the answer is often the same. DHCP that we just finished examining. The router gets its address from the ISP's DHCP server, and the router runs a DHCP server to provide addresses to the computers within the NAT DHCP router-controlled home network's address space. If all datagrams arriving at the NAT router from the wide area network have the same destination IP address, specifically that of the wide area network side interface of the NAT router, then how does the router know the internal host to which it should forward a given datagram? The trick is to use a NAT translation table at the NAT router and to include port numbers as well as IP addresses in the table entries. Suppose a user sitting in a home network behind host 10.0.0.1 requests a web page on some web server, port 80, with IP address 128.119.40.186. The host 10.0.0.1, let's say that's a laptop, assigns the source port number 3345 and sends the datagram into the local area network. The NAT router receives the datagram and generates a new source port number 5001 for the datagram, replacing the source IP address in the datagram with its own wide area network side IP address of 138.76.29.7. In other words, it replaced that IP address 10.0.0.1 with 138.76.29.75. And it also replaces the source port number of 3345 with that new source port number 5001. Now this datagram has a public global IP address. When generating a new source port number, the NAT router can select any source port number that is not currently in the NAT translation table. Note that because a port number field is 16 bits long, the Network Address Translator Protocol can support over 60,000 simultaneous connections with a single wide area network side IP address for the router. Network address translation in the router also adds an entry to its NAT translation table. The web server, unaware that the arriving datagram containing the HTTP request has been manipulated by the NAT router, responds with a datagram whose destination address is the IP address of the NAT router and whose destination port is 5001. When the datagram arrives at the NAT router, the router indexes that NAT translation table using the destination IP address and the destination port number to obtain the actual IP address 10.0.0.1 and the actual destination port number 3345 for the browser in that laptop. NAT has enjoyed widespread deployment in recent years. But we should mention that many purists in the IETF community loudly object to NAT. First, they argue that port numbers are meant to be used for addressing processes, not for addressing hosts. Okay, we've already talked about port numbers and how they're used in TCP. This violation can cause problems for servers running on the home network since, as we have seen in Unit 2, server processes wait for incoming requests at well-known port numbers. Second, they argue, routers are supposed to process packets only up to layer 3. Third, they argue, the NAT protocol violates the so-called end-to-end argument. That is, hosts should be talking directly to each other without interfering nodes modifying IP addresses and port numbers. And fourth, They argued that we should use IPv6 to solve the shortage of IP addresses, rather than recklessly patching up the problem with a stopgap solution like NAT. But like it or not, NAT has become an important component of the Internet. And furthermore, it works pretty well. Yet another major problem with NAT is that it interferes with peer-to-peer applications, including peer-to-peer file sharing applications and peer-to-peer voice over IP applications. Recall from Module 2 that in a peer-to-peer application, any participating peer, A, should be able to initiate a TCP connection to any other participating peer, B. The essence of the problem is that if peer B is behind a NAT, it cannot act as a server and accept TCP connections. This NAT problem can be circumvented if peer A is not behind a NAT. In this case, peer A can first contact peer B through an intermediate peer C, which is also not behind a NAT, and to which peer B has established an ongoing TCP connection. Peer A can then ask peer B via peer C to initiate a TCP connection directly back to peer A. Once the direct peer-to-peer TCP connection is established between peers A and B, the two peers can exchange messages or files. This hack is called connection reversal and is used by many peer-to-peer applications for NAT traversal. If both peer A and peer B are behind their own NATs, the situation gets a little trickier, but can be handled using application relays like we saw in Skype in Unit 2. NAT traversal is increasingly provided by Universal Plug and Play, which is a protocol that allows a host to discover and configure a nearby NAT. Universal Plug and Play requires that both the host and the NAT be Universal Plug and Play compatible. With Universal Plug and Play, an application running in a host can request the NAT mapping between its private IP address, private port number, and the public IP address and public port number for some requested public port number. If the NAT accepts the request and creates the mapping, then the nodes from outside can initiate TCP connections to public IP addresses, public port numbers. Furthermore, Universal Plug and Play lets the application know the value of the public IP address and the public port number so that the application can advertise it to the outside world. As an example, suppose your host behind a Universal Plug and Play enabled NAT has the private address of 10.0.0.1 and is running BitTorrent on port 3345. Also suppose that the public IP address of the NAT is 138.76.29.7. Your BitTorrent application naturally wants to be able to accept connections from other hosts so that it can trade chunks with them. You remember our discussion about BitTorrent much earlier. To this end, the BitTorrent application in your host asks the NAT to create a hole that maps 10.0.0.1 port 3345 to 138.76.29.7 port 5001. The public port number 5001 is chosen by the application. The BitTorrent application in your host could also advertise to its tracker that it is available at 138.76.29.7 port 5001. In this manner, an external host running BitTorrent can contact the tracker and learn that your BitTorrent application is running at 138.76.29.7 port 5001. The external host can send a TCP send packet to 138.76.29.7 port 5001. When the NAT receives the send packet, it will change the destination IP address and port number of the packet to 10.0.0.1 port 3345 and forward the packet through the NAT. In summary, Universal Plug and Play allows external hosts to initiate communication sessions to NATed hosts, either using TCP or UDP. NATs have long been a nemesis for peer-to-peer applications. Universal Plug and Play, providing an effective and robust NAT traversal solution, may be their savior. This concludes our exploration of the IP protocol, which is responsible for addressing. So this is a great time to take a break. Go over your notes, review this video, update your study guide, and when you're ready, come on back for the next lesson.